Hello everyone, hope you are doing well. Welcome to the online platform Civil Techno Breaks. Guys, here we will tune for the instantaneous decoding of conceptual knowledge in the field of civil engineering, where study elaborates decoding the earth to build a better world. Today we will go through the core concepts of importance of geology in sustainable infrastructure in the view of civil engineering. This is based on the three basic components, that is resources, then urbanization and climate resilience. So resources efficiency, where utilizing locally sources or locally available geologically appropriate materials to drastically reduce transportation emissions and project cost. Second one, underground urbanization, that is the subsurface activities where safely utilizing deep rock space for transit, storage and utilities to preserve surface ecosystems and reduce urban footprint. And third one, most important, climate resilience, where designing the foundations to withstand shifting geological baselines such as altered groundwater tables, increased pore water pressure, and extreme weather and coastal erosion. So, engineering geology promotes efficient use of natural resources where proper geological planning which reduces environmental impacts. Underground development requires detailed geological understanding, geological assessments which improves the climate resilience of infrastructure. So sustainable infrastructure which is depends on this integrity of geology with engineering design and applications. Geological considerations based on some foundations are, that is shallow footing, pile foundation and mat foundation. In shallow footing, shallow and competent bedrocks are required where ideal for massive quartzite or unweathered granite with high compressive strength. But for pile foundations, deep bedrock under weak soils, so that we can use to bypass thick weak alluvial clays and anchor directly into deeper stable strata as shown in the picture. And third one will be the mat foundation, which is inhomogeneous or we can say that the compressible soils where which distributes the structural load widely to prevent differential settlement or displacements in uneven geologies. So foundation design depends on the bearing capacity of soil and rock with reference to its types and characteristics. Geological conditions which determine whether the shallow or deep foundations are required based on some project point of view also, where weathered and fractured rock zones may reduce foundation stability. Groundwater conditions influences the settlement and bearing performances of soil and rock. The detailed geological investigations are most important and required to improve foundation safety and durability concerns. Geological considerations for the structure like dam, where massive construction work will come in with reference to some precise surveying methodologies. So based on some bearing capacity of soil and rock which is available beneath to that rock or beneath to that wall of the dam, then fault zones and permeability functions. So dam foundations which require strong and stable rock formations. Permeability of rock masses must be evaluated to control seepage. Fault zones and fractures are can weaken the dam foundations, so that fault zones dams must be avoid active faults or undergo extreme engineered reinforcement to survive potential displacements or deformations. Reservoir induced water pressure may influence rock stability. Detailed geological investigation which ensures the long term dam safety. Permeability, where highly fractured strata or soluble rocks which allow water leakage, generating dangerous uplift pressure beneath the dam. Based on some bearing capacity, the rock must support the massive compressive stress of the concrete plus the reservoir water which is stored inside. Massive limestone provides superior strength as compared to the thin lava flows. Means we can select a geological strata for the dam which is a granite or we can say the basalt rock which is more harder and suitable. Next one will be the tunneling point of view. Tunnel stability depends on the rock strength and the geological structures, where primary stressors and specific hazards are most important, where the pressure is acting inward, that are the vector pressure or we can say the lithostatic load. That lithostatic pressure, where the immense weight of the overlying rock column acting on the tunnel roof in downward direction as per the gravity. Structural orientation, where tunnels driven perpendicular to the strike of rock beds are significantly safer and which are more stable than those driven parallel to the strike planes. So what is the specific hazard point of view? Joint spacing, groundwater conditions. For the joint spacing, closely spaced horizontal joints are of great concern in tunneling point of view. And second one will be the water under high hydrostatic pressure can flood excavations and destroy rock cohesions. Means the tunnel stability depends on rock strength and geological structures basically. The fault, joints, folds, weak zones, these are all the geological components which affect the excavation safety. Groundwater inflow may create serious construction challenges or damages. Geological investigations which help determine tunnel alignment and support requirements. Topographical conditions, or we can say that the lithological influences, excavation methods and support systems. Geological considerations for the highway construction point of view. There are two considerations, panel A and panel B. Panel A is the stable condition, panel B will be the unstable condition. So stable condition, where a stable cut, that is rock strata dipping away from the highway cut. Gravity anchors the rock bed into the earth and minimal risk of sliding because the whole rocks are stable and hard. But in panel B, the rock strata or joints deeper into the highway cut and gravity pulls the unsupported rock beds towards the rock, or we can say that the roadway side, that is the instability condition. Means for a large joint dipping into a highway cut is the site of a potential landslide. Means we have to avoid the panel B condition. So highway alignments should avoid unstable geological formations. Slope failures often occur when rock layers dip towards excavation cuts. Weathered rocks and loose materials increase landslide risk. Geological mapping, which helps identify safe route alternatives, and proper slope stabilization, which provides or which are dependent on the geological conditions naturally occurred. Here, the geological hazards which are affecting engineering works, most important and harmful impact on the infrastructure of the earthquakes, then landslides, rock fills, and subsidence. So earthquakes creates ground shaking or creating vibrations which may provide the structural instability. Landslides and rock falls threaten the transportation and infrastructural systems, that is roadways, highways or alignments of roadways. Ground subsidence may occur due to geological or groundwater related causes. That geological hazards vary in severity and probability of occurrence. So probability of occurrence on x-axis with reference to the impact of on infrastructure on y-axis. So we can take earthquakes are of probability of occurrence is minimum, but the damages are more, where probability of occurrence is more of subsidence, where damages are less. Likewise, we can study the geological hazards. So hazard assessment is an essential component nowadays for engineering planning and construction point of view, so that the safety factor or the person's or livelihood depends on that project may take the advantage for the same. For case study point of view, we can take the geological failure in construction, where the blueprint and the reality. So the ignoring geological conditions can lead to engineering failures. So we are engineers, we must be more focused with reference to the engineering construction point of view, so that the coming or in future failures may restore, or we can say that mitigate. Inadequate investigation or improper investigation may overlook weak zones and unstable slopes. Groundwater and weathering can accelerate failure mechanisms. The geological assumptions must be verified through field investigations. Lessons from failures improve the future engineering practices, where the project, the oversight, the result and the correlation. So three main conditions are there. A massive concrete arch dam constructed in a deep, or we can say steep mountain valley in the blueprint, which is the project. The oversight condition is that failure to recognize the precise orientation of foliation planes and the presence of weak clay seams that lost all cohesive strength when pore water pressure increased, so that the foundation anchors are provided and rock abutment where the reservoir level is there, an arch dam will be constructed in between the valley portion. Result is that the catastrophic gravity sliding of the entire rock abutment into the reservoir, displacing the water over the dam, means the reality is that the dam wall gets crackened and the whole water which is stored within the upstream side is affected due to that huge landslides, that is massive landslides which is seen in the image number 2, and the whole dam it gets crackened, or dam wall will get crackened and the whole water is may create the flood situation. So the core lesson is that the most advanced engineering mathematics cannot save a structure built on a improper geology, or we can say that miscategorized geological foundations. Stay tuned guys, happy learning.